before the first light ignited, before time learned how to flow, before space found room to expand, what was nothing? And was it ever truly empty? The Big Bang is often told as the birth of the universe, but a quieter, deeper question is usually left behind. Did something exist before that moment? Could nothing breathe? Could it wait? Could it carry the seed of everything that would ever be? Leave your thoughts in the comments. Do you believe in nothing? Or in something far more silent and hidden? And now we begin with the first question. Did anything exist before the universe began? What if the most unsettling thing about the Big Bang is not the explosion of creation, but the quiet question it leaves behind, like a door half open in a dark hallway? Before the universe began, was there truly nothing at all? We say the beginning as if it were a simple pin on a timeline, but the moment you lean closer, the timeline itself starts to blur, like ink running in water. Because the Big Bang is not merely an event that happened inside space and time. In our best understanding, it is tangled up with the birth of space and time themselves, which is why Stephen Hawking famously compared the question to what is north of the North Pole, a poetic reminder that some questions may be shaped by the limits of the map rather than the limits of reality. And yet, even when a question might be ill-formed, it can still be profoundly useful. It can still pull us forward. Here is the strange beauty of it. In everyday life, time feels like a river. It runs whether we watch it or not. It carries birthdays, regrets, and sunrise after sunrise. But in Einstein's universe, time is not a universal drumbeat ticking the same for everyone. It stretches. It slows. It bends. Put a clock on a fast-moving ship or deep in a strong gravitational field, and it will not agree with a clock at rest, high and far away. Time is physical. Time has texture. And once you accept that, the Big Bang becomes even more mysterious, because you begin to suspect that time might not be the stage on which the universe appears. Time might be one of the actors, walking onto the stage at the same moment the curtain rises. To make this less abstract, imagine a storybook that begins on page 1. Now imagine that page 1 is also the invention of pages. Before page 1, there is not a blank page. There is no page at all. That is how some cosmologists describe the Big Bang. Not an explosion into empty space, but the origin of the very concept of earlier and later. BF says, it is a difficult idea because our minds evolved to navigate seasons, distances, and the slow arithmetic of survival, not the edge of physics. We are creatures who can feel hunger and nostalgia, but we cannot directly feel the beginning of time. We can only infer it, like archaeologists reading ash layers in the earth and reconstructing a fire they never saw. And yet, the evidence for a hot beginning is not a myth. It is written across the sky. The cosmic microwave background, that faint afterglow bathing the universe, is like the oldest photograph we possess, a baby picture of reality itself. It whispers that the cosmos was once dense, hot, and opaque, and then cooled into clarity. It tells us that there was a time when light could not travel freely, when the universe was more like a thick fog than a star-filled cathedral. Then, as atoms formed and the fog lifted, light finally streamed forward, and it has been traveling ever since, arriving now as a cold microwave echo. This is why I always tell people, the Big Bang is not just a theory you read in a book. It is a place the universe has left a fingerprint, and we are living inside that print. But the fingerprints do not answer the deepest question, because the fingerprints begin after the moment when our equations themselves begin to tremble. As we push backward toward the earliest instance, gravity grows extreme, energies grow colossal, and the smooth language of space-time starts to crack. General relativity, Einstein's magnificent description of gravity, predicts that if you wind the clock backward far enough, you reach a singularity, a point where density becomes infinite and the equations stop making sense. That is not a satisfying ending. It is a warning sign. It is nature telling us we have reached the border of a theory, not necessarily the border of existence. So, scientists propose bridges. One bridge is inflation, the idea that the universe, in a fraction of a second, expanded at a furious pace, smoothing and stretching the newborn cosmos. Alan Guth once described the universe as the ultimate free lunch, because inflation can create enormous amounts of space from a tiny initial region. It is a breathtaking concept, reality widening faster than light can cross it, not because anything is moving through space too quickly, but because space itself is multiplying. Picture a tiny dot of dough suddenly swelling into an enormous loaf, and raisins that were close together now separated by vast distances, not by running apart, but by the dough expanding beneath them. Inflation helps explain why the universe looks so uniform on large scales, and why tiny fluctuations could later grow into galaxies. But inflation also raises its own haunting questions. What triggered it? What field powered it? And if inflation happened once, could it happen repeatedly, birthing other regions, other universes, beyond our horizon? Another bridge is the idea of a bounce. Instead of an absolute beginning, perhaps the universe once collapsed, reached an extreme state, and rebounded into expansion. In that story, before exists, but it belongs to a previous chapter. Quantum gravity models sometimes hint at this possibility, suggesting that the singularity is not a real physical point, but a sign that space-time becomes granular, with a smallest unit of structure preventing infinities. If that is true, then the Big Bang is less like creation from nothing and more like a phase change, like water freezing into ice or ice melting back into water, except the substance-changing phase is space-time itself. Now, let's slow down and talk about nothing, because the word is a trap. In ordinary speech, nothing means absence, emptiness, a room with no furniture and no sound. But physics uses the word differently. The quantum vacuum is not a blank canvas. It is more like a restless sea. Fields still exist. Energy still fluctuates. Particles can briefly appear and vanish in ways that are measurable. So when some people say the universe could arise from nothing, they may not mean philosophical nothingness. They may mean a quantum state with laws, fields, and possibilities already present. That is not nothing in the way a poet means nothing. It is a kind of pregnant silence, a quiet that is still humming. This is where the conversation becomes more than technical. It becomes personal, because it confronts the way our minds demand origins. We crave a first cause, the way we crave a first sentence in a story. But the universe may not owe us that kind of narrative satisfaction. As Einstein once put it, the most incomprehensible thing about the universe is that it is comprehensible. A Everstade CH. I read that not as a victory speech, but as a confession of wonder. We can understand enough to build telescopes that read the oldest light, enough to model the birth of elements, enough to trace the rise of galaxies. And yet, at the very edge, the universe turns into a riddle again, as if reminding us that comprehension is not possession. There is also a humility hidden here that I think is deeply educational. If time can begin, then cause itself becomes slippery, because causality depends on time's arrow. We ask what caused the Big Bang the way we ask what caused a fire, but fires happen inside time. If time is part of what came into being, then the cause may not sit before in any ordinary sense. It might be a deeper rule, a boundary condition, a relationship written into the structure of reality. James Hartle and Stephen Hawking suggested that the universe may be finite yet without an edge, like the surface of a sphere. On a sphere, you can travel forever without falling off, yet there is no boundary line that says, here the world ends. Well, have says, if the universe is like that in time, then looking for the first moment might be like looking for the first latitude on Earth. The question may feel natural, but the geometry refuses to cooperate. And still, I do not think we should stop asking, because the value of these questions is not only in the answers we might one day obtain, the value is in what they do to us while we carry them. They expand our sense of scale. They teach intellectual honesty, the courage to say, we do not know yet, without turning that ignorance into despair. They teach precision. They teach awe. Carl Sagan once said, we are a way for the cosmos to know itself. In a did it is stepped side, whether you take that as poetry or as a scientific metaphor, it contains a practical lesson. Curiosity is not a luxury. It is a method of becoming larger than our fears. My personal takeaway is simple. The universe does not merely contain mysteries. It trains us through them. It teaches us to think more carefully, to speak more precisely, to hold uncertainty without panic. When you stand at the edge of time and ask what came before, you are not just studying cosmology. You are practicing a form of mental courage. So here is the promise of the journey ahead. We will take the Big Bang seriously as a physical theory supported by evidence. And we will take its unanswered edge seriously as a frontier. We will look at what our best observations can tell us, where they fall silent, and which bold ideas attempt to speak in that silence without pretending to be final truth. And with that, we step into the next part of the story, the first doorway we must pass through together. The question that sounds simple and yet can rearrange your entire sense of reality. Did anything exist before the universe began? What if the oldest thing you will ever see is not a star, not a galaxy, but a whisper of heat coming from every direction at once? What if the universe left behind a childhood photograph, and we have been learning to read its faint smile ever since? When people ask about the early universe, they often imagine an explosive firework in a dark void. But the truth is stranger and more intimate. The early universe was not an object inside space. It was space itself becoming possible, then stretching, then cooling, then learning the first rules of structure. And the evidence is not hidden in philosophy alone. It is written in light that still reaches your skin, and in elements inside your blood, and in the quiet patterns that modern instruments can map with almost reverent patience. In my mind, the early universe is like a sealed room filled with blinding steam. Everything is there, energy and potential and raw ingredients, but you cannot see across the room because the fog is too thick. For a long time after the Big Bang, the cosmos was exactly like that. Photons kept colliding with free electrons, scattering again and again, like a crowd that will not let a messenger pass. No matter where light tried to go, it was interrupted. So, the universe had heat, but not clarity. It had motion, but not visibility. It had a future, but not yet a view. Then the temperature dropped. The steam began to thin. Electrons finally settled into stable partnerships with nuclei, forming neutral atoms. This is the moment the universe became transparent, the moment the cosmic fog lifted. And when that happened, light finally traveled freely, racing outward in every direction like a secret released. We still see that light today, not as a visible glow, but as the cosmic microwave background, a faint afterimage stretched by expansion into microwaves. It is, quite literally, the oldest light we can observe, a baby picture of the cosmos, not painted by an artist, but printed by physics. Here is where the wonder becomes practical, because that ancient glow is not perfectly smooth. It has tiny variations, slightly warmer and slightly cooler spots, like the ripples on a pond after a pebble has been dropped. Those ripples matter. They are the first hints of gravity choosing favorites, the first suggestion that some regions were a little denser than others, the first draft of what would become galaxies, clusters, and the vast cosmic web. If you want an everyday analogy, imagine baking bread. At first, the dough looks uniform, but give it time, and small pockets expand, bubbles form, structure emerges. The cosmic microwave background is the photograph of the dough before the loaf rises. It shows the seeds, not the finished cathedral. This is also the point where the story becomes deeply educational, because it teaches a lesson many people miss. Nature does not need dramatic differences to create dramatic outcomes. A whisper can become a storm. A fraction of a percent in density, spread across an ocean of space, can eventually become the Milky Way. This is why the early universe is such a powerful mirror for human learning. Small habits, small choices, small curiosities, repeated over time, can grow into entire new worlds inside a person. The cosmos is not only a place, it is a teacher. We also have another kind of evidence, quieter but even more intimate. Look at the elements. Hydrogen, helium, a little lithium. These are not just ingredients, they are fossils. In the first minutes after the Big Bang, conditions were so hot and dense that nuclear reactions forged the lightest elements. This primordial recipe can be calculated, predicted, and checked against what we actually measure in the universe today. When the numbers align, it is not just a technical success. It is a kind of cosmic memory confirmed, as if the universe kept its receipts, as if it can still show us exactly what it bought at the beginning of time. And then there is expansion itself, the grand heartbeat. We see distant galaxies moving away, their light stretched into longer wavelengths, redshifted like a siren fading into the distance. This is not a metaphor. It is measurable. It is repeatable. It is one of the reasons the Big Bang model remains so successful, because it does not only tell a beautiful story, it predicts what the sky should look like, and then the sky, again and again, answers back. Still, there is a reason this topic never stops haunting people, because every piece of evidence we collect is also a boundary line. The cosmic microwave background is a wall of sorts. Not a wall in space, but a limit in time. It marks the earliest moment we can see with light, because before that, light could not travel freely. So when someone asks, what happened before, the honest scientist must say, we cannot look there directly. We must infer, model, and imagine with discipline. And that tension between what we can see and what we long to know is where the best science lives. This is where the great voices of science feel less like lecturers and more like fellow travelers. Albert Einstein once said, "The most incomprehensible thing about the universe is that it is comprehensible." 84 won it. That line lands like a bell in the chest because it captures the miracle of evidence. The early universe is not only vast, it is legible. We are tiny, but the cosmos speaks in patterns that minds like ours can learn to translate. And Carl Sagan, with his gentle insistence on wonder, reminded us, we are made of star stuff, once-a-darias, which is not merely poetry. It is observational astronomy becoming personal. The early universe forged the first elements. Stars later forged heavier ones, and those atoms became oceans, bones, and thoughts. When you study the first light, you are studying your own deep ancestry. Modern instruments have expanded this conversation. Space telescopes can now peer into the epoch when the first galaxies ignited, catching faint infrared signals that have traveled for more than 13 billion years. This is like hearing the echo of a first word spoken in a dark cathedral, long after the speaker has gone. When astronomers find unexpectedly bright galaxies very early in cosmic history, it forces new questions. Did structure form faster than we expected? Were stars born more efficiently in the beginning? Or are we missing a piece of the physics that links those tiny ripples in the microwave background to the full-grown galaxies we see later? These are not failures of science. They are the living edge of it. A good theory is not a prison. It is a scaffold. And sometimes the universe asks us to build higher. There is also a beautiful human lesson here, and it is one I return to again and again. We tend to think knowledge is a straight path, but the early universe teaches a different rhythm. First, there is darkness, then a faint glow, then structure, then questions, then deeper questions. Certainty is not the goal. Understanding is. And understanding often begins with humility. Stephen Hawking offered a simple, unforgettable reminder that feels like advice for science and life at the same time. Remember to look up at the stars and not down at your feet. Thanks for watching. Because the sky does something to the mind. It reorders your priorities. It shrinks your ego. It enlarges your patience. So when I speak about the early universe and observable evidence, I do not only mean satellites and spectra and equations. I mean a relationship. We are in conversation with the oldest light in existence. We are decoding a message that has been traveling since the universe was young enough to still be called a newborn. And every time we sharpen our instruments or refine our models, it is as if we are cleaning dust from an ancient inscription carved into the fabric of reality. The universe does not shout its origin. It whispers it. Reality leaves traces. Truth can be approached, and even when the beginning is hidden behind a veil, we can still learn where the veil starts, what it is made of, and what it implies. That is not a small achievement. That is the human spirit at its best. Curious, careful, and brave enough to admit what it does not yet know. And now, with that first image in mind, the sky as a living archive and the cosmic microwave background as its earliest page, we can take the next step. Because the most tempting question still waits at the threshold, like a shadow with a heartbeat. If the oldest light we can see is already after the beginning, then what, if anything, came before the universe began? What if almost everything you have ever loved, every sunrise you have ever witnessed, every human story ever told, is floating on top of an invisible ocean you cannot touch? And what if that ocean is the real architecture of the universe? When we look up at the night sky, it feels honest. Stars glitter like facts. Galaxies glow like proof. Yet the deeper astronomy peers, the more it discovers a strange imbalance. The universe is not mostly made of the things that shine. It is mostly made of things that do not. Here is the hook that should make your mind sit up straight. If you could scoop up every atom in every star, every planet, every cloud, every human body, and weigh it all together, you would still be holding only a thin foam on the surface of the cosmic sea. Because the most careful measurements we have suggest ordinary matter is a small minority, and the rest is a pair of mysteries we call dark matter and dark energy. I want you to feel what that means, not as a statistic, but as a quiet shock, because it tells us something humbling. The universe is not obligated to be understandable on first glance. Carl Sagan once reminded us, "We are made of star stuff." One say, that line is beautiful, but it is also incomplete in a way that makes the story even more dramatic. Because stars themselves appear to be only the glittering frosting on a much larger cosmic structure. a structure built from something that does not emit light, something that refuses to show its face. So how did we stumble into this strange conclusion? We did not find dark matter by chasing it like a hunter. We found it the way you find the presence of wind, not by seeing the air itself, but by watching what the air makes move. Imagine a city at night after fresh snow. You cannot see the wind directly, but you can see the drifts it shapes. You can see the swirling patterns on the ground. You can feel it in the way branches bend. Dark matter is like that. An unseen presence inferred from its fingerprints on motion. One of the most vivid examples comes from galaxy rotation. A galaxy is not a still painting. It is a spinning city of stars. And if gravity came only from the matter we can see, the outer stars should orbit more slowly, like distant horses on a carousel losing their grip. Instead, the outer stars race around faster than they should. It is as if the galaxy is wrapped inside a hidden halo, adding extra gravity like an invisible scaffold. This is one of the reasons scientists began to take dark matter seriously. Another example is gravitational lensing. Think of space as a calm, dark lake. Drop a heavy stone into it and the surface curves. Now shine a flashlight across that lake and the beam will bend as it passes over the curve. In the real universe, galaxies and clusters are the stones, and light is the beam. We see background galaxies stretched into arcs and smeared into luminous commas. And when we map the amount of bending, we often find there is more gravity present than visible matter can account for. Something massive is there, even when nothing bright is. This is where I always pause, because the emotional lesson hides inside the math. We are living in a cosmos that reveals itself indirectly, a cosmos that teaches patience, a cosmos that forces us to become detectives rather than tourists. And then there is dark energy. If dark matter is the hidden scaffolding that helps structures form, dark energy is the whisper that pulls everything apart. It is the reason the expansion of the universe is not merely continuing, it is accelerating. To picture this, imagine raisin bread in the oven. As the dough rises, every raisin moves away from every other raisin. No raisin is the center. The space between them simply grows. Now imagine the oven turning up on its own. So the bread does not just expand steadily, it expands faster and faster. That is what the universe appears to be doing on the largest scales. The discovery of this acceleration in the late 1990s landed like thunder, because gravity should slow expansion down. Gravity is the great collector. Gravity is the instinct of matter to gather. And yet the universe was behaving as if it had another instinct. An expansive urge, a stretching pressure written into space itself. Albert Einstein famously said, "The most incomprehensible thing about the universe is that it is comprehensible." One for Mater. I have always loved that sentence because it carries a paradox. Yes, we can understand a great deal, but we also keep discovering that understanding has edges. And at those edges, the universe feels less like a solved puzzle and more like a living poem. So what are we really saying when we say dark energy? We are saying we do not know what the engine is. We only know the direction it pushes. We measure it through its effect on distance and time, like hearing footsteps in the hallway without seeing the person. At this point in the story, people often feel two emotions at once: awe and discomfort. Awe, because the universe is deeper than we imagined. Discomfort, because our intuition is built for a world of chairs, rivers, and weather. Not for a cosmos where 90-something% of the contents are invisible to our senses. But that discomfort can be transformed into a powerful kind of education, because it teaches a lesson about how knowledge grows, not by confirming what we already believe, but by allowing reality to correct us. If you need a human scale analogy, try this. Imagine you walk into a vast cathedral at night. You can see only what your small candle illuminates. A few pillars, a patch of stone floor, a hint of an arch above you. You might be tempted to think the building is only what you can see. But then you notice something. Your candlelight casts shadows that curve in unexpected ways. You hear echoes that suggest empty space far beyond your little circle of light. You feel a draft that implies unseen corridors. In that moment, you begin to understand the cathedral is larger than your senses. Dark matter and dark energy are like those echoes and drafts. They are the universe telling us, gently but firmly, that the room is bigger than our lantern. There is a quote I return to whenever this topic starts to feel too abstract. Neil deGrasse Tyson put it simply, "The universe is under no obligation to make sense to you." By the Vakshnagrevicenses. Some people hear that and feel shut out. I hear it and feel invited, because it means confusion is not failure. Confusion is the beginning of real learning. My personal view is that these mysteries are not embarrassing gaps in science. They are signs of science working as it should. When you reach the edge of what you can measure, you do not pretend you have certainty. You name the unknown. You build better instruments. You refine your questions. You become more honest. And there is a quiet spiritual value in that honesty, even for people who are not religious. Because it trains humility, it trains wonder, it trains the ability to live with unanswered questions without turning away. In a world full of loud certainty, the cosmos teaches a softer strength, the strength to say, "We do not know yet," and to keep going anyway. The universe is not just a collection of objects. It is a relationship between what exists and what can be known. Dark matter and dark energy remind us that reality is often revealed through consequences rather than appearances. They remind us to pay attention to motion, to patterns, to subtle shifts in the background. They remind us that the most important forces in your life may not be the ones you can see, but the ones you can feel through their effects. And that brings us back to the central promise of this journey. If we are brave enough to follow the evidence where it leads, if we are patient enough to sit with the mystery, then the darkness is not an ending. It is a doorway. So tell me in the comments, does it unsettle you that most of the cosmos is invisible? Or does it comfort you to know there is still so much left to discover? And as we move forward, keep this question in your mind like a quiet star. If the universe is mostly made of unseen ingredients, what else have we mistaken for emptiness, simply because we have not learned how to see it yet? What if the standard model of cosmology is not a finished cathedral, but a lantern carried through fog? What if the cracks people whisper about are not failures, but invitations? Tonight I want to take you straight to the frontier, where modern observations begin to press gently, persistently, against our most trusted picture of reality. For a long time, the universe seemed to behave like a well-rehearsed symphony. Gravity gathered matter into galaxies, dark matter acted like an unseen stage rigging, and dark energy, whatever it was, kept the whole performance expanding outward. The story felt stable enough that many of us started to treat it like background music. But science has a way of turning the volume up on what we assumed we understood. And lately, the instruments have become so sensitive that they can hear tremors beneath the melody. One of the most haunting examples comes from the cosmic microwave background, that ancient afterglow often compared to a photograph of the universe as an infant. Newer maps have become sharper, not just showing where the primordial weather was dense or thin, but how it flowed. Suzanne Staggs captured the shift with a line that lands like a door opening in a dark room. Before, we got to see where things were, and now we also see how they're moving. Hi. That single sentence contains an entire lesson in humility. Because when you start seeing motion as well as position, you stop thinking of the early universe as a static picture on a wall. You start feeling it as a living ocean, a slow tide of matter and light, still echoing with the first breath of creation. Here is an image to make it tangible. Imagine you walk into a forest after snowfall. At first, you only see the drifts, the shapes. Then you notice the wind has carved ripples, and you realize the storm was not random at all. It had direction, pressure, rhythm. That is what these new observations do. They reveal subtle patterns that help test our best model with a kind of merciless tenderness. And so far, the model holds up remarkably well. But in the act of testing, we also discover where the questions begin. The most dramatic questions now gather around dark energy. For decades, the simplest idea was that dark energy is constant, like a built-in property of space, steady as a silent drumbeat. But recent analyses have raised a possibility that changes the emotional temperature of the entire cosmic story. Arjun Day said, "The DESI results tantalizingly hint at an evolving dark energy. I was never body," and Mustafa Ishaq went further, calling the finding probably the most important result about cosmic acceleration since its discovery in 1998. 18 Zions. If those hints solidify, the universe stops looking like a machine with one setting. It starts looking like a living thing whose mood can change over time. To picture why that matters, imagine you are in a car on a long open highway at night. You feel the engine pulling you forward, and you assume the pressure on the pedal will remain the same forever. Then, slowly, you notice the pull is weakening. Maybe you are still moving fast, but you are no longer accelerating the way you were. That single change forces new questions. Will the car eventually coast? Will it slow? Will it stop? In cosmic terms, will expansion keep accelerating forever? Or could it soften, stall, or even reverse in some distant epoch? It is not just a technical detail. It is the difference between an endless thinning of reality and a future where gravity might someday gather the universe back into a tighter embrace. Now let me be clear in the way a responsible science storyteller must be. Hints are not verdicts. Signals can shift with new data, new calibrations, new cross-checks, but the educational value is already immense because it shows you how science actually moves. Not by clinging to a model as identity, but by testing it until it either breaks or grows stronger. Richard Feynman once said, "Science is the belief in the ignorance of experts." The Edis. That is not disrespect, it is discipline. It means we treat even our finest achievements as provisional, because reality does not owe us comfort. And here is where the story becomes almost meditative, because we can watch human knowledge behaving like a mind in mindfulness practice. You hold an idea gently. You observe it patiently. You let evidence move through it like breath. If the idea survives, it becomes clearer. If it fails, you release it without shame. That is the posture cosmology is being forced to adopt right now, because the universe is offering us sharper measurements than ever before. There is another kind of challenge, not from the subtle behavior of dark energy, but from the sheer architecture of the cosmic web. On the largest scales, cosmology expects a kind of statistical sameness, a homogeneity when you zoom out far enough. Yet astronomers keep reporting enormous structures that look, at least at first glance, too large and too coherent to fit the simplest expectations. The universe may be more textured than our averaging instincts. Think of it like looking at Earth from a plane. At high altitude, the surface seems uniform, but as you descend, patterns emerge. Rivers, ridges, coastlines, scars of ancient impacts. Some patterns are real, some are illusions created by our perspective, and the only way to know is to keep descending with better instruments and better methods. When people ask me what I personally take from these challenges, I always return to a quiet truth. A model is not the universe. A model is a poem we write in mathematics, a disciplined metaphor that helps us predict what we will see. And the moment we forget that, the moment we worship the metaphor, we lose the plot. I have watched audiences fall into two traps. One trap is panic, as if any tension in the data means everything is collapsing. The other trap is denial, as if a beautiful model must be protected from revision. The mature response is calmer than both. It is curiosity. It is the willingness to stand at the shoreline of the known and let the waves rewrite the sand. This is why I find these developments so valuable for education. They teach that uncertainty is not the enemy of knowledge. It is the atmosphere knowledge breathes in. If you want a simple human-scale analogy, think about medicine. A doctor does not abandon anatomy because a new scan reveals a rare variation. They refine their understanding, and that refinement saves lives. In the same way, cosmology does not abandon its foundations because measurements tighten. It learns how to speak more precisely about what it already suspected, and it remains open to surprises that could reshape the story. And there is something almost spiritual in that openness, because it asks us to live with a rare kind of honesty, to admit that the universe is not obligated to match our expectations, to accept that what we call dark may simply be a word for the parts of reality we have not learned to name yet, to remember that every great leap in understanding began as discomfort, as a mismatch between what the mind wanted and what nature quietly insisted upon. So here is the promise I want you to carry into the rest of this video. We will follow the new observations with respect. We will treat the theories with seriousness, but not devotion. And we will translate the stakes into images you can feel. Because when the data suggests that dark energy might evolve, or when new sky maps reveal motion where we once saw only a static pattern, we are not just updating numbers. We are watching humanity learn how to read the oldest writing in existence, the faint handwriting of the early cosmos etched in light. And I want to end this opening reflection with a question that is simple enough to haunt you. If the universe is still changing the rules by which it expands, then what else, right now, is quietly changing in the dark, waiting for us to notice? What if the first sunrise in the universe did not rise over an ocean or a mountain range, but over a darkness so deep it had never known a single spark? What if the earliest light was not a gentle glow, but a fierce announcement that existence had finally found its voice? When we say cosmic dawn, we are naming a moment that feels almost human. A child opening its eyes for the first time. A quiet room suddenly remembering it has windows. For hundreds of millions of years after the Big Bang, the universe was filled with hydrogen and helium, and yet it was strangely silent in the language of light. Not empty, not dead, but waiting. The way a seed waits inside winter soil, carrying a whole forest as a secret. Then, slowly, gravity began to gather the thin gas into knots. Not with drama, but with patience. And in those knots, the first stars may have ignited, massive and brief, like matches struck in a windstorm. Their light did more than illuminate. It changed the rules of the night. It began to burn away the fog of neutral hydrogen that filled space, the same way morning sun thins the last mist over a field. This is why cosmic dawn matters, because it is the chapter where the universe learned to be visible. Before galaxies had names, before planets had homes, before life could even dream, the cosmos began practicing the art of structure. It is one thing to have matter. It is another thing to have architecture, filaments, clumps, disks, and halos, the first blueprints of the cosmic web. Edwin Hubble once wrote, "Equipped with his 5 senses, Man explores the universe around him and calls the adventure science. There wasn't a stand. I love that line because cosmic dawn is the moment our senses fail, and our instruments become our new eyes. We are trying to hear a lullaby sung more than 13 billion years ago through a wall of distance that time itself has built. And this is where the James Webb Space Telescope feels almost like a mythic artifact, not because it breaks physics, but because it extends our reach into an era that used to be only theory. Webb does not simply look far away. It looks far back. It captures infrared light that began as ultraviolet starlight, stretched and softened by expansion, like a shout turning into a whisper over an endless canyon. To picture this, imagine a campfire on a distant ridge. Up close, it crackles bright and blue. From miles away, it looks redder, dimmer, more ancient. Now multiply that distance until the ridge is the edge of the observable universe, and the campfire is an early galaxy. That reddening is not just color, it is time made visible. Webb has shown us galaxies that appear shockingly early, brighter, and more mature than many models expected. This is not a small inconvenience for cosmology. It is a deep and productive discomfort. Because if large, bright galaxies appear only a few 100 million years after the Big Bang, we must ask how the universe assembled complexity so quickly. Did stars form more efficiently than we thought? Did gas cool faster than our simulations allow? Are we misreading the masses because dust and black holes are playing tricks with light? Or is there something subtle in the early conditions that we have not yet learned to recognize? Here is one example that makes the mind snap to attention. Think about the Milky Way as a city built over a long history, with layers of neighborhoods, old stone, and newer glass. Now imagine finding a distant city in the universe, when the universe itself was still a toddler, and yet the skyline is already crowded with bright towers. That is what some of these early detections feel like. Not impossible, but astonishing. Like finding an oak tree where you expected only grass. Another example. If you have ever watched a time lapse of frost forming on a window, you know how patterns bloom from near invisibility into intricate lace. Cosmic dawn is like that, but the window is space-time, and the frost is the first network of stars and galaxies. Tiny differences in density, almost nothing, become everything. A slight excess here, a slight deficit there, and suddenly the universe is no longer uniform. It is storytelling. Some researchers have called the first stars the holy grail of early chemical evolution, because those stars began with the simplest ingredients and yet forged heavier elements in their cores. That point matters for anyone trying to understand why we exist in a universe that can make planets, oceans, and breathing things. Hydrogen and helium can make stars, yes, but carbon, oxygen, nitrogen, iron, those require stellar lives and stellar deaths. The first stars likely lived fast and died violently, scattering the first metals like a cosmic pollen. Without that, later generations of stars would have lacked the materials to build rocky worlds. Carl Sagan famously said, "We are a way for the cosmos to know itself." One phrase. Cosmic dawn is one of the reasons that statement does not feel like poetry alone. It feels like a description of lineage. Because when we look for the first light, we are not merely hunting facts. We are tracing ancestry. We are trying to understand how a universe that began simple learned to become complicated enough to wonder about itself. And yet, there is a humbling limit built into this search. Even Webb cannot show us everything. It can bring us closer to the edge of the first galaxies, closer to the first star formation, closer to the era when darkness first began to retreat. But there will always be a boundary where light cannot help us, where theory must take the lead. Cosmic dawn is a frontier, and every frontier has fog. Not the fog of ignorance, but the fog of distance, physics, and finite time. I want to add a personal thought here. When people hear first galaxies, it is easy to treat them like museum pieces behind glass, precious but irrelevant to daily life. But I think Cosmic Dawn is secretly one of the most practical stories we can tell, because it teaches how big outcomes can emerge from small beginnings, not in a motivational slogan way, in a literal, physical way. Tiny fluctuations in a nearly smooth early universe become the scaffolding for everything we see now. It is a lesson in patience, in compounding, in the quiet power of time. And it teaches something else, more intimate. In the beginning, the universe was not arranged for comfort. It was hot, then cold, then dark, then violent, then luminous. Order had to be earned, step by step, generation by generation, through processes that took hundreds of millions of years. When I remember that, I feel a kind of calm, because it suggests that clarity often arrives late. Light does not always come first. Sometimes it comes after long waiting, after gravity has gathered the scattered pieces into a place where ignition becomes possible. So when we talk about cosmic dawn, we are not just describing the universe's first starlight. We are describing the moment structure began to win over chaos. The moment the cosmos began to write with brighter ink. The moment the night sky, in some early sense, started becoming a sky at all. And that leads to the question that keeps tightening its grip the longer you sit with it. If the first galaxies appear earlier and brighter than expected, what does that say about the hidden efficiency of nature? What else might be forming beyond the limits of our current assumptions, in eras we have not yet properly imagined? What other surprises are waiting inside the dark, like unlit rooms in a house we thought we had already mapped? Because the deeper we look, the more the universe seems to do something almost mischievous. It answers one question and replaces it with three better ones. It gives us a glimpse, then dares us to interpret it. It shows us the first hints of dawn, and then asks whether we truly understand what dawn is. So stay with me, because next we are going to follow that first light even closer to its source. We will ask what the earliest stars might have been like, how they transformed the surrounding hydrogen, and why this ancient sunrise still echoes through the universe we inhabit today. What if the universe is not as smooth and evenly balanced as we were taught? What if the sky is hiding scars so large that our favorite assumptions begin to wobble? And what if the patterns we call random are actually the universe trying to tell us a story? For a long time, modern cosmology has carried a quiet promise in its pocket. Step far enough back, zoom out far enough, and everything averages out. No special directions, no special places, no cosmic center stage. I failed see. This is the spirit behind the cosmological principle, the idea that on the largest scales, the universe should look broadly the same. It is not a poem, but it has the elegance of one. It says that when you pull away from the local drama of galaxies and clusters, the cosmos becomes calm, like an ocean seen from high above. And for decades, that promise seemed to hold. The cosmic microwave background looked astonishingly uniform, with only tiny ripples. Those ripples felt like the gentle fingerprints of a young universe. They became the seeds of everything, the first hints of the cosmic web. Filaments, nodes, and voids, like frost spreading across a window pane in slow motion. It is breathtaking that we can even speak this language. As Albert Einstein once said, the most incomprehensible thing about the universe is that it is comprehensible. Because Haggis, but then we started mapping deeper and wider, and the calm ocean began to show unexpected swells. Not little waves, but colossal shapes that seem to stretch across distances so vast they stop behaving like ordinary structures. Eyeways. Imagine you are looking at a forest. Up close, the trees are messy, tangled, unpredictable. But you expect that if you climb high enough, the forest becomes a texture, evenly spread across the land. Now imagine climbing higher and higher, only to find a single spiral-shaped line of trees looping across half a continent. It would not feel like just a forest anymore. It would feel like a message. That is the emotional shock these ultra-large structures provoke. They are not simply big, they are uncomfortably big. Big enough to make you ask whether our models are missing a step, or whether nature is less shy about grand patterns than we assumed. Some of the reported features, like the Big Ring, suggest a shape so immense that even describing it strains the mind. A ring, or perhaps a corkscrew, traced by galaxies and clusters across more than 1 billion light-years. Nearby, in cosmic terms, another sweeping formation, sometimes described as an arc, spanning multiple billions of light-years. And these are not alone. Astronomers have discussed other vast arrangements, walls and chains, that feel like continental plates of galaxies. Each time a new map reveals a new Leviathan, the same question returns with different clothing. Is this real structure, or are we seeing patterns where none exist? To make this intuitive, picture a cloud of gnats in sunlight. From a few feet away, you see swirls and streams, almost like tiny rivers in air. From far enough away, you expect it to become a blur, evenly spread. But what if, from far away, you still see a clear spiral, a clear loop, a clear band that keeps its identity no matter how far you zoom out? That persistence is what troubles cosmologists. Because on the largest scales, the universe is supposed to become statistically bland, not boldly calligraphic. Now, there are careful voices here, and they matter. Science does not panic, it measures. A structure can look dramatic in a limited data set. Selection effects can carve illusions into the sky. Human pattern recognition is powerful, and sometimes too eager. This is why the most responsible posture is patience. More data, better statistics, independent confirmations. In my view, this is the hidden beauty of the scientific method. It is a discipline of humility. It teaches you to fall in love with questions without rushing to marry the first answer. Still, even the possibility of these megastructures does something profound to the imagination, because it touches the boundary between two ways of seeing reality. On one side is the comforting universe, governed by simple assumptions that scale smoothly. On the other side is the strange universe, where new patterns emerge at scales we thought would wash everything away. And if that boundary shifts, even slightly, it changes what we think we are doing when we do cosmology. The cosmological principle is not merely a technical detail, it is the quiet stage direction behind much of modern inference. When we estimate the age of the universe, when we model expansion, when we talk about dark matter scaffolding and dark energy pressure, we are leaning, at least gently, on the idea that the cosmos is not playing favorites at the largest scales. So, when the maps hint at structures that are too coherent, too extended, too shaped, it feels like discovering a crack in the foundation of a cathedral. The cathedral may still stand, and the crack may be superficial, but you cannot unsee it. There is also a deeper emotional layer. These vast structures invite a kind of existential vertigo, because we are used to thinking of ourselves as small in the universe, a planet around a star, in a galaxy, in a cluster, in a supercluster. But the moment you see a wall or ring of galaxies stretching across billions of light years, you feel small in a different way, not merely in size, but in certainty. It is the sensation that the universe might be more textured than our clean narratives allow. This is where I like to bring in a second voice, one that reminds us why this pursuit matters. Carl Sagan said, "Somewhere, something incredible is waiting to be known." .com. In the context of ultra-large structures, that something may not be a new object. It may be a new principle, or a subtle correction, or a deeper understanding of how early fluctuations evolved into the cosmic web we inhabit. Perhaps these structures are rare statistical outliers, the universe's version of a freak wave. Perhaps they are artifacts of how we sample the sky. Or perhaps they hint at early universe physics we have not yet fully grasped, a whisper from inflation, or a relic of exotic ingredients that left faint organizing marks. To keep it grounded, imagine you are baking bread. You mix flour and water, yeast and salt. At first it looks uniform. Then slowly, bubbles form, pockets of air, networks of holes. If you slice the loaf, you see structure that grew from tiny differences. Now imagine a loaf where a single tunnel runs almost the entire length, a continuous corridor of emptiness. You would suspect something special happened during the rising. Not magic, but conditions. Temperature, mixing, timing. The universe, in a sense, is a loaf that has been rising for billions of years, and the cosmic web is the crumb pattern. If we find a corridor too long, a loop too coherent, we ask what conditions allowed it. That is not a crisis in the theatrical sense. It is a crisis in the original Greek sense, a turning point, a moment where observation forces refinement. And this is where Edwin Hubble's old line feels quietly appropriate. Equipped with his five senses, man explores the universe around him and calls the adventure science. It's not might of eyes. The adventure is not just the discovery of new things, but the discovery that our old frames were too small. When a map surprises us, it is not humiliating. It is a gift. It means the universe still has leverage over our assumptions. My personal takeaway is simple, and it has shaped how I think about education and wonder. We often teach science like a finished monument, but real science is a living conversation between what we expect and what nature actually does. The cosmological principle is powerful because it is simple and because it works astonishingly well. But its power can tempt us into treating it like a law of taste rather than a hypothesis that must constantly earn its place. When the sky hints at something bigger than our expectations, the correct response is not to abandon rigor. It is to deepen it, to sharpen the questions, to make our models brave enough to be wrong and precise enough to be corrected. So, if these enormous structures hold up under scrutiny, they may not overthrow our understanding. They may refine it. They may teach us that the universe can be statistically uniform and still contain rare, dramatic forms. Or they may teach us that our earliest assumptions about initial conditions need a subtle twist. And if they do not hold up, if they dissolve under better data, that lesson is equally valuable, because it will remind us how easily the mind can turn incomplete information into certainty. Either way, the story is worth telling, because it returns us to the central human posture beneath all cosmology, a posture of awe, disciplined by doubt. We look outward, and the universe looks back, not with answers, but with patterns. And the patterns ask us to grow up intellectually, to become more careful, more curious, more honest. So here's the question I want to leave hanging in the air like a distant, steady star. If the cosmos truly becomes smooth when you zoom out, why does it keep sketching these immense shapes across the deep sky? And if it does not become smooth, what does that say about the story we thought we understood, and the much older story the universe may still be trying to tell? What if the biggest mystery in cosmology is not how everything began, but whether beginning is even the right word. Most of us grew up with the Big Bang as a clean starting gun, a dramatic flash in a dark theater, and then the universe pours outward like a symphony released from silence. But the deeper you listen, the more you notice that physics speaks in conditional verbs, in careful maybes, in doors that open only to reveal another door. So, here is the question that hooks the mind and refuses to let go. If the universe has a birthday, what was the room like before the candles were lit? The traditional story says time and space arrive together, and in that view, asking before is like asking what lies north of the North Pole. It is a beautiful comparison because it turns the question back on us. Maybe the problem is not that the universe is hiding an answer, but that our language is using the wrong map. And yet curiosity is a stubborn, holy thing. Even if time began, we still wonder what kind of reality could give rise to time, the way a shoreline gives rise to waves. This is where theories beyond the standard Big Bang step in, not as replacements carved in stone, but as lanterns carried into fog. One lantern is cosmic inflation, the idea that the universe expanded outrageously fast in its earliest breath. Alan Guth, the pioneer most associated with inflation, once described it with a blunt kind of wonder, calling it a free lunch because it suggests the universe can create vast structure from a tiny starting budget. The phrase lands because it feels almost mythic, a cosmos that pays for its grandeur with the strange accounting of gravity. To picture it, imagine drawing a tiny dot on a balloon and then inflating the balloon so violently that the dot's neighborhood becomes an entire horizon. You did not travel faster than light across the rubber, and yet distances between points grew faster than light because the surface itself stretched. Inflation does not answer everything, but it changes the emotional texture of the beginning. It suggests the universe may have had a growth spasm, an almost biological surge, like a seed splitting open faster than you can blink. And if inflation happened once, the next question naturally follows. Could it happen again and again? That leads to the unsettling elegance of eternal inflation and the multiverse, where inflation never fully ends, and pocket universes bud off like bubbles in a cosmic foam. Some physicists treat this as a serious possibility, others as an idea that slips beyond what we can ever test. But as a mental image, it is hard to forget. A night sky that is not the whole sky, only one lit window in an endless hotel. Another lantern is the cyclic universe, where the Big Bang is not the first chapter, but the latest sunrise in a chain of sunrises. Here the universe is not a one-time firework, but a breathing organism, expanding, thinning, cooling, and perhaps resetting in ways we have not yet learned to read. Roger Penrose, a giant of modern theoretical physics, has argued for a version of this called conformal cyclic cosmology, where the far future of one cosmic era can be mathematically reshaped into the next beginning. Whether you accept the model or not, the poetic logic is striking. The end becomes so empty, so stretched, so smooth, that it starts to resemble a beginning. It is like watching a river widen into an ocean until the distinction between river and ocean loses meaning. To make it tangible, think of a song played so softly and so slowly that its final note can be reinterpreted as the first note of a new song. In that story, before the Big Bang is not nothing. It is the echo of an earlier universe that has faded into a kind of pure geometry. Then there is the Big Bounce, often discussed in approaches like loop quantum cosmology, where the universe contracts, reaches a dense state, and rebounds. This is not the classical singularity of infinite density, but a quantum-guarded limit, a trampoline rather than a bottomless pit. Picture a basketball compressed in your hands. The more you squeeze, the more it pushes back, until at last it springs away. In bounce cosmologies, quantum effects play the role of that pushback, preventing the equations from falling into infinity. The emotional power of the bounce is that it rescues the question of before from meaninglessness. There was a before, and it may have left fingerprints. Tiny anomalies in the distribution of matter, subtle patterns in ancient light, whispers in the polarization of the cosmic microwave background. Not proof, not yet, but possible places to look. And then we meet the most unsettling word of all: nothing. Physicists sometimes say the universe could come from nothing, but in modern physics, nothing rarely means what ordinary speech means. A vacuum in quantum theory is not a dead stage. It is a restless sea where fields jitter and fluctuations appear and vanish. As the late Stephen Hawking famously put it, because there is a law such as gravity, the universe can and will create itself from nothing. One of the time. Many people read that line and feel either revelation or resistance, but either way it forces a redefinition. Nothing in this context is not a blank void with no rules. It is a state with laws, a framework, a potential. So, the philosophical tension remains. If laws exist, is that really nothing? This is where I personally feel the humility of the subject. We might be arguing over the meaning of a word while the universe is operating on a level that does not care about our vocabulary. And yet vocabulary matters because it shapes how we think, and how we think shapes what we dare to test. That is why I return again and again to a line attributed to Einstein, a sentence that has survived because it feels like a compass. The most incomprehensible thing about the universe is that it is comprehensible. Batizing. Even if you have heard it 100 times, let it land again. We live inside a reality that can be understood, at least partly, by minds made of matter. And that fact, to me, is more mysterious than any single model. Carl Sagan offered another famous line that does not solve the equations, but steadies the heart. We are made of star stuff. BASAS. It reminds us that these theories are not cold abstractions. They are attempts by the universe to understand itself through us, through carbon-based brains staring into the dark. Now, beyond these well-known frameworks, there are more speculative ideas, some radical, some mathematical, some almost mythic in tone. Cosmic strings, for example, are hypothetical defects in space-time, like cracks in ice stretched across the cosmos. If they exist, they might leave gravitational signatures or patterns in the way galaxies align. You can picture a sheet of fabric with a tight thread sewn into it. The thread pulls the fabric into a subtle crease, and anything rolling nearby drifts toward that crease. No one has confirmed cosmic strings, but the point is not certainty. The point is that the universe might still contain relics of phase transitions, ancient scars from a time when forces separated, like colors splitting through a prism. And then there are ideas that challenge not only the beginning, but the assumption that there was a single beginning at all. Some proposals imagine multiple bursts, multiple creation events, or a universe that refreshes itself in ways that mimic expansion. Even when these ideas fail, they serve a purpose. They pressure test our confidence. They force the standard model to prove why it deserves its throne. In my view, that is the real educational value of going beyond the traditional Big Bang. Not that we trade one dogma for another, but that we learn how science actually breathes. It expands, it contracts, it revises, it admits ignorance without surrendering to it. When you watch cosmologists debate inflation, bounces, cycles, or multiverses, you are watching disciplined imagination at work. You are watching people walk a tightrope between wonder and proof. And there is a personal lesson hidden in that method. Our own lives often feel like they began with one event, one turning point, one irreversible origin story. But look closer, and you see cycles, rebounds, hidden prehistories, quiet influences that came before the moment you thought everything started. The universe may be teaching us, gently, that beginnings are rarely simple. They are thresholds, not points. They are transformations, not miracles pulled from empty air. So when you ask what existed before the Big Bang, you are not just asking about cosmology. You are asking about the nature of explanation itself. You are asking whether reality is a single line with a first dot, or a circle, or a spiral, or something stranger than any shape the mind can hold. And that brings us back, smoothly, to the first door we must open before any of the others will make sense. Did anything exist before the universe began? In the next part, we will step closer to what science can actually measure, and where measurement fades into inference, and where inference becomes the most careful kind of storytelling. What if the greatest mistake we make about the Big Bang is assuming it was a door that opened from absolute nothing, rather than a page we turned without seeing the chapters behind it? In the popular telling, the universe begins like a match struck in a dark room, and everything that ever was floods outward from a single instant. It is a powerful story, clean and dramatic, and it fits neatly inside the human craving for beginnings. But the deeper you travel into cosmology, the more that neatness starts to soften at the edges, like ink in water. Because the word nothing is not a simple emptiness in physics. It is a concept with teeth, a silence that may still hum. Carl Sagan once wrote, "Somewhere something incredible is waiting to be known." AD. That line matters here, because the incredible might not be a new galaxy or a new particle, but a new way of thinking about origin itself. And if you have ever stood at night beside a quiet sea, you know how misleading silence can be. The surface looks still, yet beneath it, tides move, currents speak, and the ocean remembers storms you cannot see. One bold alternative is the idea that the universe did not begin, it bounced. Imagine a great cosmic breath, an inhale that becomes a collapse, an exhale that becomes expansion, and between them, a moment of pressure so extreme that the rules we trust begin to blur. In some quantum gravity-inspired pictures, what we call the Big Bang could be the rebound of an earlier universe that contracted into a dense state and then sprang outward again. To make that feel less abstract, picture a slow-motion video of a trampoline. A heavy object sinks it down, stretching the fabric until it looks like it must tear, and then the tension pushes back, launching the object upward. In that metaphor, the trampoline is space-time, and the bounce is not magic, it is a response. The point is not that the universe is literally a trampoline. It is that a beginning may be a turning point rather than a first moment. Another daring idea is cyclic cosmology, where the universe is not a single story but a library of stories, one after another, each ending, preparing the stage for the next beginning. One of the brand is up again to the Nunavik. Roger Penrose, one of the most celebrated mathematical physicists of our era, has explored a version of this through conformal cyclic cosmology, suggesting the remote future of one universe might, in a strange way, resemble the starting conditions of another. Whether or not his specific model is right, it invites a haunting image. Time becomes less like an arrow and more like a horizon that keeps reforming, as if the cosmos is forever learning how to restart itself. Then there is the ekpyrotic, or brain collision family of ideas, where the Big Bang is not an explosion from nothing, but a collision event between higher dimensional surfaces, like vast cosmic sheets drifting in a space beyond our perception. If that sounds too far from everyday life, try this. You cannot see the wind, but you can see what it does to a field of grass, how it lays it down in waves, how it shapes motion into patterns. A higher dimensional event, in this analogy, would be the wind, and our observable universe would be the grass. We would not see the cause directly, but we might see its fingerprints in the patterns it leaves behind. Some proposals go in a different direction and suggest that the Big Bang was not a single unmatched event at all, but part of a sequence, like rare sparks in a long night. Instead of one creation moment, there could be multiple sudden episodes, transient singularities, brief floods of energy that appear, reshape the expansion, and vanish. Think of a calm lake disturbed by occasional stones. Each splash sends rings outward, each ring intersects with others, and from above, you might mistake the whole surface pattern for a single grand design. The lesson here is practical and humbling. When we see a curve in the data, we are always tempted to believe it is one simple story, but nature often writes with overlapping chapters. And of course, hovering over all these ideas is the question of whether before has meaning at all. Stephen Hawking famously offered a comparison that still stings with elegance, asking what lies north of the North Pole. The point is not to be clever. The point is to reveal how our intuition can fail when we push it beyond the territory it evolved to navigate. Time might not be a river that always existed. It might be a feature that emerges, the way a melody emerges from vibrations, not present as a thing until motion and structure make it possible. This is where I find myself returning, again and again, to intellectual honesty as a kind of quiet spiritual practice. Richard Feynman warned, "The first principle is that you must not fool yourself, and you are the easiest person to fool." In cosmology, self-deception often wears the mask of certainty. We want a single answer we can frame and hang on the wall, but the universe may not be built for our comfort. Or as the biologist J.B.S. Haldane put it, the universe is not only stranger than we imagine, it is stranger than we can imagine. It'd say, so what do we do with these bold alternatives? We treat them the way an experienced navigator treats unfamiliar stars, with curiosity, with discipline, and with the willingness to revise the map. We ask what each model predicts, where it could leave traces, and how new measurements might distinguish poetry from reality. And we let the process educate us, not by handing us a final answer, but by training the mind to live gracefully inside uncertainty. If there is a lesson I carry from this, it is that not knowing is not failure, it is the beginning of real thinking. The cosmos does not owe us simplicity, but it does reward patience. And maybe the most human response to the question of what came before is not to force a conclusion, but to keep the question alive, like a lantern in a vast cave. Because when we stare into the idea of nothing, we are also staring into ourselves. What we call the beginning of the universe might be less like a single flash, and more like a rhythm we have only just started to hear. So tell me in the comments, which possibility feels most plausible to you? A bounce, a cycle, a collision, a sequence of rare cosmic sparks, or a before that does not exist at all? And as we move forward, keep that question burning gently in the background, because the next part of our journey is where theories meet evidence, where the sky itself becomes the test. What if the word before is the most human thing we ever invented? A lantern we carry into a cave where time itself has no floor. We live inside clocks. We taste life in sequences, morning then night, inhale then exhale, birth then memory. So when we hear that time may have begun with the Big Bang, our minds rebel, because rebellion is how imagination protects meaning. If there was no time, we ask, what could before possibly point to? Stephen Hawking once suggested that asking what happened before the Big Bang may be like asking what lies north of the North Pole. It sounds clever until you feel the sting of it, because it turns our favorite doorway into a wall. And yet, even walls have textures, and physics has a strange habit of turning walls into horizons, and horizons into invitations. Picture a map of Earth drawn by candlelight. At the edge of the ink, the ocean does not end. The paper ends. In the same way, before might not be a forbidden realm, but a sign that our current language, and maybe our current equations, have reached the edge of their paper. Albert Einstein wrote to a friend that the distinction between past, present, and future is only a stubbornly persistent illusion. If time is not the sturdy river we feel it is, then before might be less a location and more a relationship, like the shadow cast by a lamp you have not yet seen. Then comes the second wound in the question, sharper and older. Was the Big Bang creation from nothing, or continuation from something else? The word nothing sounds simple, like an empty room, but physics does not treat it that way. Even what we call vacuum has structure, restless fields, statistical tremors, a kind of quiet potential. Lawrence Krauss famously framed it this way, that nothing in modern physics is not the nothing of philosophy. And that distinction matters, because it means the universe might have arrived not from absolute emptiness, but from a stage so subtle we confuse it with absence. Try an image that your senses can hold. Imagine a calm lake at dusk. From far away it looks perfectly still, yet up close it is alive with ripples, insects, microcurrents, the soft gossip of water against stone. If you only saw it from the hill, you might swear it was nothing happening at all. But nothing can be busy in ways our distance cannot resolve, and the early universe may have been that kind of lake, a silent surface hiding motion. Still, some thinkers propose something even more dramatic than a restless vacuum. Roger Penrose has explored the possibility that our universe is one in a long chain of cosmic eras, where the far future of one becomes, in a deep mathematical sense, the beginning of the next. In that picture, the Big Bang is less a first breath and more a turning of the page, a transition so extreme it looks like a beginning from where we stand. Other ideas, like bounce cosmologies, suggest a previous universe collapsed, compressed, and then rebounded, as if gravity itself inhaled the cosmos and then released it again. It is a haunting thought, because it makes the universe feel less like a one-time miracle and more like a heartbeat. But how would we ever know? We cannot point a telescope at before the way we point one at a galaxy, because light itself may not carry messages across that boundary. So the question becomes quieter and more practical. Could we find indirect evidence? Not a photograph, but a fingerprint. A faint bruise in the cosmic microwave background, a subtle asymmetry, an odd pattern of polarization, a statistical whisper that does not fit the simplest story. Like walking into an ancient temple and seeing the stones are aligned to a star. You do not prove the star built it, but you realize a mind was thinking in a larger geometry than ordinary life requires. And that brings us to the border that every honest science communicator must name without killing the wonder. Where does observation end and theory begin? The line is not a fence, it is a gradient. On one side, we have data that bites back, measurements that can embarrass our favorite ideas. On the other side, we have mathematics, disciplined imagination, models that must be beautiful enough to unify, yet humble enough to be wrong. Richard Feynman gave us a hard truth that I return to like a meditation bell. It doesn't matter how beautiful your theory is. It doesn't matter how smart you are. If it doesn't agree with experiment, it's wrong. Intelliations. And yet, Without theory, we would not know what to look for, or how to listen when the universe speaks in a dialect of numbers. My own view is simple, and it is a lesson worth keeping. Before might be meaningless in the strictest sense, and still meaningful in the human sense, because it reveals the shape of our curiosity. Whether the Big Bang was a first spark or a doorway from something older, the deeper education is the same. We are learning to distinguish the limits of reality from the limits of our descriptions. We once thought the horizon was the end of the world, until we sailed and discovered it was only the end of our sightline. Perhaps cosmology is teaching the same humility on a grander sea. So now I leave you with the question that makes this more than a lecture, it makes it a shared search. Which scenario do you find most plausible?